I'm starting with the question that we did in the GGT, but then got stuck. Arctan. Okay, so we had the antiderivative of x times arctan x. And we started by using integration by parts. And we have this set up when we do integration by parts. And what we do is we pick in our expression a u of x and a v prime of x. And then we find the v of x, the antiderivative of v prime of x, and the derivative of u of x, which is u prime of x. And we plug it into this formula, which gives us what I have here. And where we got stuck was calculating this integral, which turns out not to be that hard. There's a little trick. And what that trick is that you can add 1 and then subtract 1. So this is exactly the same expression here, because all we've done is added 0, which doesn't change anything. And then we break apart the fraction, and what we get is 1 minus 1 over x squared plus 1 dx. And what this becomes is you can split the antiderivative across subtraction, so you get the antiderivative of 1 minus the antiderivative of x squared plus 1 dx. But this is one that we know is common. It's the derivative of arctan x, so what we get is x minus arctan x. Alright, so you just plug this into here and simplify. I won't do those details, but that's how to proceed from here. I can't believe I didn't see it. And don't forget plus c. Next we're going to do 7D on the practice midterm that was requested. So this one's substitution rule that you need to use. And so you'll take your u of, well, we won't call it u of x, I'll just call it u. We'll set u equal to 1 over x. And then by substitution rule, we need to find out what du should be. And du is the derivative of this times dx. And so take the derivative of this, and what you will get is 1 over x squared, and then add a dx. Okay, so now we substitute. I'll do this in 2 steps, actually. So we substitute 1 over x for u in the sign u, and what we have left over is 1 over x squared dx. And so what we have here is almost this, but the negative sign is different. So in order to compensate, when we substitute, we have a negative du. Pull the negative sign out, and we can integrate this. The antiderivative is negative cos u, because cos u, when you take the derivative of it, you get negative sign. So we need to take it. The antiderivative will be negative cos u. So it's negative cos u plus c. So what we have is cos u plus c, but we want it in terms of x because that's how we started. And so we just go back up and find out what u is, and u is 1 over x, so it's cos 1 over x plus c. And that is our antiderivative. Okay, so now I'm going to do question 9 from the final, the practice final. Just parts A and B, because part C is just plugging in values or finding values, or finding the input for a certain output for the expressions that we're going to find here. So what we need to do in question 9 is use antiderivatives to solve differential equations. So what we're given is v prime of t equals negative 2. And we want to find what v of t is. And we're also given information that v of 0 is 14. So we use the antiderivative here. V prime is with respect to t, so let's take the antiderivative with respect to t on both sides. And what we get is vt on this side, and on the other side we have negative 2t, plus some constant. Now we can use our initial value to find out what that constant is. We just plug in 0, and what we get is c, because negative 2 gets killed, and this is equal to 14. So our c is equal to 14, which gives us the full expression for Vt, negative 2t plus 14. Okay, so for part B, we're given that dp over dt is equal to Vt, which is equal to negative 2t plus 14. So we take the antiderivative with respect to t on both sides. We get dp over dt. dt equals the integral of negative 2t plus 14 dt. Negative t squared, because the derivative of t squared is 2t plus 14t, plus, of course, a c. And what is this? This is p of t. This is just a fancy way of writing p prime of t right here. And so we need to solve for c, so we plug in 0, and for this part we're given that p of 0 is equal to 0, and we get c is equal to 0. And so our expression p of t is equal to negative t squared plus 14t. Here's another antiderivative that involves a fraction and the exponential function. And this one turns out not to be too hard when you use substitution rule. You set your u to be square root of x, and you get this expression of du. And now we're going to note that 2 du is equal to 1 over the square root of x dx. So we plug the u into the eu here, and we note that this is what's left in our expression, which is exactly this. So we replace this with eu 2 du, right, what we got here, and we know that that the antiderivative of e to the u is itself. So we get 2 e to the u plus c, which is equal to, replace the u with what we started with. We get 2 e square root of x plus c. Alright, so I made up an integral to suit our purposes. I was asked to give a complex integral with a fraction involving addition at the bottom. So here we go. And complex, not complex numbers, but with trigonometric functions. And so here we're going to use substitution rule. We're going to set u to be sine x plus 1, and of course that makes our du cos x dx, because that's the derivative of that, and then we times it by dx. And so we substitute to find out what this integral is going to be. And I'm going to remove the 0 and pi from here, because this is just what we're thinking. Because when we change the variable, we're no longer taking the integral on those numbers. So what do we have? We have a u below, and we have to do sine x goes to u minus 1, because you subtract 1 and you get sine x, so it's u minus 1 up here, times cos x dx, which is exactly our du. Alright, so what is this? This is the integral of 1, because we're going to split the fraction here, and then 1 over u du, which is equal to u minus ln u. Alright, we put u back in, and what do we get? We get sine x plus 1 minus ln sine x plus 1. Alright, so this is, and this will have a plus c, but when we take the integral, we're going to add c and subtract c, so it disappears. And so the integral of this is equal to sine x plus 1, this is just sine x plus 1 minus ln sine x plus 1 evaluated from 0 to pi. So this is our f of pi minus f of 0. And so for the first evaluation, we get sine pi plus 1 minus ln sine pi plus 1. And we're going to subtract the evaluation at 0, which is sine 0 plus 1 minus ln sine 0 plus 1. Alright, there's some simplification in order. Sine of pi is 0. Ln of 1 is 0. Again, sine of 0 is 0. Sine of 0 is 0. Ln of 1 is 0. So what we have left is 1 minus 1, which is 0. So I created a pretty nice integral.